It's a great pleasure to be speaking at this event. Maxime's work has truly informed my career in many times, starting perhaps from the moment in which he presented us with his whole-crossing formula. And it seemed to describe a lot of physical phenomena in supersymmetric quantum field theory. And then, well, exploring why this was the case was really a crucial step for me. It led me to ask questions about supersymmetric quantum field theory and defects in these theories, which well, kept me occupied for years. And even recently, in the last couple of years, essentially all of my projects touch in some way are based on or inspired by work by Maxime. And because of this, I sort of found myself unable to make a reasonable editorial decision. And so I will essentially tell you about everything I've been doing the last few years. The presentation might be a bit telegraphic, but I'm very happy to explain things more in detail after the talk. So the main subject, as the title is saying, are sort of twisted supersymmetric quantum field theories. Now, I'm not going to be able or want to define for you what a supersymmetric quantum field theory is. The only thing you need to know is that there is some object which has some Grassmann-Hopf symmetries, and very often you can find an nilpotent Grassmann-Hopf symmetry. And what a twisted quantum field theory is essentially defined as the cohomology of the original quantum field theory with respect to this differential, with respect to this odd symmetry. The result is a new quantum field theory, which is much simpler. It's simple enough that it's often mathematically tractable and in a rigorous way. Part of the reason is that while a generic quantum field theory is very analytic, it depends on the choice of metric on your manifold. It has correlation functions, which are very complicated functions of positions of the observables, of the local operators. After the twist, you get theories which are usually holomorphic-topological. Which means that they don't care about a metric on space-time. They only care about a local splitting of space-time into some holomorphic and some topological directions. Let's say R to the T and C to the H. So the special case of topological theories is probably very familiar to a lot of you. Topological field theories are described in the language of categories, DG categories, homological algebra, and so on. Holomorphic topological theories should be presumably formalized in the language of holomorphic topological factorization algebras. Or categories.
These underlying manifold with relations with some sort of holomorphic structure, yes?
I think so, yes. That's right. So for my purposes, essentially what this means is that I have some coordinates, say x1 to xt, z1 to zh, and z bar 1 to z bar h locally. And I want the data of a mixed differential, mixed Dalbo-Deram differential, something like sum of dxi del over del xi plus d z bar I alpha del over del z bar alpha. So roughly, what's going to happen is that you can study correlation functions of local operators. But the correlation functions do not really depend on the topological directions and do not really depend on the anti-holomorphic directions. So very schematically, derivative of operators in the topological or anti-holomorphic directions vanish, or perhaps are Q exact. So vanish in cohomology of Q. Okay, so as I said, depending on the choice of number of topological and homomorphic directions, you get a variety of interesting mathematical structures. And at the same time, physically, this is interesting because these twisted theories capture pieces of the original quantum field theories. For example, there are a lot of questions that are very hard in quantum field theory, even asking what's the space of possible quantum field theories, or what's the space of possible defects of some sort in a quantum field theory. These are very difficult questions. After you twist, you can ask what's the space of possible twisted theories and try to recognize in there which ones could come from a physical theory. For example, in a case where you have 2D TFT, meaning T is 2 and H is 0. Well, we heard during the previous talks many times mentions of Calabi-Yau categories, or the G categories, or infinity categories, and so on. This is the mathematical language you would use to study a theory of this sort. If I want to talk about some supersymmetric quantum field theory and I don't have a Lagrangian to describe it, I don't quite know what to say about it, one thing I can do is to start by giving a Calabi-Yau category. So similarly, I would like to understand what should I give, what data should I give, how should I present a theory for more general choices of T and H. This could be an example of a question I would like to understand. As I said, there is a lot of mathematics which is explicitly or implicitly hidden in this sort of universe. I don't know, you want to study quantum groups, you want to study probably chance or not invariants, you probably want to study a Chern-Simons theory, which is a topological theory in 3 dimensions, again, not holomorphic. You like vertex algebras or chiral algebras, well, you want to study T equal to 0, H equal to 1. You want to study not homology, well, 4-dimensional topological theories are probably going to be your friends, and so on. Now, I want to give a simple example of Maxim's work on the subject that influenced me. So we mentioned early in some of the previous talks the formation quantization.
Excuse me.
Yes.
That's a stupid question. Can one add also quaternions?
There are some situations where actually you need a complex symplectic form. For example, if you have H equal to 2, T equal to 0, which is the holomorphic twist of 4-dimensional n equal 1 theories. Classically, you could define them on any complex surface, but in practice, quantum effects force you to have a complex structure, a symplectic form, a complex symplectic form. So yes, so I lied a little bit here. I apologize.
When H equal to 0, it's a vacuum sector of physical theory. When T equals 0 and H not 0, is there a simple derivation?
Oh, it depends. So suppose you want to study a theory which has real physics in it. 4-dimensional n equal 1 super Yang-Mills. is a very interesting theory because it has confinement. We would love to be able to say anything about this theory. This theory does have an nilpotent supercharge, but it doesn't give you a topological twist. It gives you an h equal to 2, t equal to 0 theory. This is pretty much the reason I got into studying these holomorphic-topological theories. Well, part of the reason is that these are theories we really want to say something about, and the standard topological twist techniques don't help. But you have an holomorphic twist. It's a beautiful theory. It has some very large symmetry, infinite dimensional symmetry algebra of Hamiltonian symplectomorphisms of C2. Can I get some physics out of it?
But that will not be something like vacuum sector of the physical theory. It will be some other sectors that can be.
Well, the thing I learned from reading Maxim papers is that the good way to think about this twisting is that the most natural observable in quantum field theories are anomalies, Hooft anomalies. So you can take a theory, deform it, and see if the BRST symmetry is still there. And the obstruction to this is going to be some brackets, some L infinity structure, some lambda brackets, or so on. That is the typical structure you'll be able to compute here. In the physical theory, it's giving you some kind of a mixed gauge supersymmetry anomaly. It's telling you that if you try to deform the theory in a way that naively preserves supersymmetry, in practice you might encounter some difficulties. And these obstructions are what are computed here. A beautiful property of Hooft anomalies, the reason we study Hooft anomalies, is that they are RG flow invariants. So if I know that the UV theory has some anomalies, so we'll have the effective low energy description for the same theory. So whatever structure I compute in these twists will have a functor from the UV to the infrared. So if I can compute anything here, it will tell me what can happen in the infrared. In this particular example, this holomorphic twist becomes mysteriously topological at one loop. This is some kind of constraint on what can happen in infrared. The infrared cannot be too rich. Otherwise, the holomorphic twist of the infrared will not be topological. So this is sort of compatible with confinement. It's a cute observation about this system. It doesn't prove confinement, but at least it proves that you cannot not confine too badly. So I think you can get physics out of these twists, and it's just very unexplored. But this is a math conference, so let me go back to math. So formality theorem.
Sim is both mathematician and theoretical physics.
That's true.
So you can do.
But the rest of the
We are okay.
Yes. So the formation quantization and the formality theorem. So these are statements that, as a physicist, I associate to the two-dimensional B model with target Cn. So concretely, it's a theory. I can write a Lagrangian. There are some fields. These fields are essentially forms which only use these components, the x and the z bar. So think of them as functions of it's actually topological. So think of them as functions of x and dx. So a sum of forms in all degrees from 0 to 2. This lives in cos number 1, in cos number 0. And this lives in cos number 1. You can think about it as a sigma model into pi t star of so the target of the B model is essentially a -1 shifted symplectic manifold. Here I'm taking just this pi t star Cn. And if you study the free theory, you can write an action, which is essentially theta I, the zeta I. If you want to make theory more interesting, you can add some interactions, which are functions of thetas and zetas. And actually, if you want to preserve ghost number, which is usually a good idea, you need an interaction of ghost number 2. So you're going to have some function of the zetas bilinear in thetas. Okay. And I can ask, is this a sensible action? It should be a BV, it's a BV action. Classically, it should satisfy some BV equation, master equation. And this turns out to be the same as the statement that a certain bivector is Poisson. I'm cutting a lot of corners here, but so classically, if you give me a Poisson bivector, you can define this B model. And quantum mechanically, there can be obstructions, there can be BRST anomalies. This equation is corrected. You can write a quantum BV equation, and then you can homotopy transfer it to sort of polynomials in pi and thetas. And the corrections to these, so quantum mechanically, you have corrections. These corrections can be computed from some Feynman diagrams. In particular, the cubic correction is computed by a loop, by a triangle. And then you have more complicated Feynman diagrams, which compute further corrections. And what Maxime proved as a step in the deformation quantization, in the formality theorem, is that these actually vanish. So you can just evaluate these Feynman diagrams and show that they all vanish, and then you learn that this theory is well defined, even quantum mechanically. And the relation to deformation quantization appears when you...
Poisson sigma mono?
Yes, yes. So the deformation quantization comes if you also study the system in R times R plus. So if you consider a boundary, not called a D-brane, you can consider a Neumann boundary condition where you set thetas to 0. And then you have local operators, which are essentially functions of theta, of zeta. Now, in the same way as you can introduce interactions in the bulk, you can also introduce the interactions in the boundary that form your boundary condition. You can add some quantum mechanical system, some vector space V, and you can add a boundary interaction, sort of an integral over the boundary of some d of zeta. D is a matrix. Is a map, is an element of matrices, endomorphisms of V valued in the zetas. Again, you can ask, is this a allowed interaction? Does this define a good system? Classically, there is a obstruction.
V is a fibrous trivial bundle?
Yeah, a trivial bundle. And if pi is 0, you find that the interaction is consistent. The boundary interaction is consistent if it squares to 0. So you get essentially a complex on Cn. You find derived coherent sheaves on Cn if you dig deep enough. But if you ask what happens if you turn on pi, well, this condition must be deformed in some way. At the leading order, you find the Poisson bracket as a correction, and then there is a sum over Feynman diagrams which gives you the star product, the deformation quantization of this Poisson variety. I wanted to mention this example in some detail because I want to stress that these sort of questions can be asked for a large class of theories of holomorphic topological type.
Also here there's also two types of propagators.
Yes, yes. So that's right. Your basic diagram will have a pi here and two Ds.
No, but propagators, there are two formality morphisms. One for you take D of argument, which I use originally, and then there was a complex valued, which took 15 years to prove that everything is okay, which was much more trivial. Alexei Fotorosyan, they make the complete proof.
I'm not.
Yes, one propagator was some product D, leading for differential of logarithm of z minus z bar, something like this.
Yeah.
And if you move two of them, they took simpler, but the proof that all things vanish is much more non-trivial. It's
Sorry. So you're saying, yes, you can do the holomorphic.
And it gives complex valued formula.
complex valued.
So you could study in 2D holomorphic theories.
No. It's both topological.
Okay.
Was topological, but you get kind of a different choice of boundary condition to define what.
I think we didn't have one parameter family actually. We'll walk after the paper.
Yeah.
So it's a question.
So is it the same theory or is it a different scheme for the same theory?
It's different scheme for the same theory.
Okay, no, sure. Right, these things.
And you get some action of this not trivial.
Yeah, these things are scheme dependent, and in different scheme, you might get different answers. And if you find that they vanish, good. If you find they don't vanish, not so good.
Vanish in a different way, yeah.
Yes, or they vanish in a different way. In recent work, we looked at similar theories. Again, you have some fields, and then you use this funny mixed Hodge Durand differential and plus an interaction. And you can ask, is this a good theory? Or are there quantum corrections to the classical constraints on the interactions? There definitely can be such corrections. You can look at the case of holomorphic theories in one dimension. These give you chiral algebras. And you can definitely check that in this situation, you get sort of corrections that come to the true bracket that come from Feynman diagrams like this. Of course, also in case of h equal to 0, t equal to 1, this is quantum mechanics. In quantum mechanics, definitely the product of operators as a sum over Feynman diagrams is called the Weil product. So quantum correction can happen. The question was, when do they happen? So we found that we can generalize Maxim proof to the case of any t greater than 2, greater or equal to 2, and any h. So as long as you have two topological directions, an analysis similar to the one of Maxim's shows that all the Feynman diagrams vanish. So
for this pure topological stories was one proof for t greater than 3 and for t equal to
yeah, so the theory, we have a proof which is very uniform. Essentially, we write the integrand as a product of a factor for each dimension, and the topological factor squares to 0. Just a combinatorial identity.
And so when h is not equal to 0, what kind of quantization theorem does it?
Right, exactly. Sadly, well, okay, I'll get there in a second. So for t equal to 1 at any h, there can be potentially quantum corrections. For example, for t equal 1 and h equal to 1, there is a true loop diagram which gives a potential correction. So you're in the bracket there is a classical bracket between the interactions, and then there is a quartic correction, and then who knows what at higher orders. Because it's true loop, although we computed it and found on 0, we haven't been able to check that you cannot get rid of it by a field redefinition. So who knows, maybe this still vanishes in some other scheme, but in our scheme definitely doesn't. Now, it is a bit of a pity because you can do deformation quantization in this theory. You can study a boundary condition which wraps C times R plus in the space-time, and you can just repeat the analysis, consider normal boundary conditions, and so on and so forth, put an interaction in the bulk. Classically, the interaction gives you a Poisson vertex algebra. This Poisson vertex algebra is trying to deform a trivial chiral algebra at the boundary by introducing some OPEs. If there was no abstraction, then it would mean that you can always quantize a Poisson vertex algebra into an actual vertex algebra. I haven't been able to find much literature on this, so I don't know if people know the possible abstractions to quantizing a Poisson vertex algebra.
So there was a paper of Tamarkin, but I think maybe there were some issues with it, where he claimed that he can quantize Poisson vertex algebra.
I see.
But I don't know what status is. Maxim, do you know what status?
No, it's not.
Because this is a potential abstraction to the quantization Poisson vertex algebra.
Yes, with this project.
Yeah. So I'm not sure it is. I mean, complete.
Partially, to remember this was before formality. It was result of eating off of Kazhdan, which is not yet translated to physics. As any by algebra can be deformed to Hooft algebra. The formulas is still absent. We don't have formulas and pattern diagram calculus.
Isn't that so there's a statement about three-dimensional topological? Okay, so there are no abstractions.
Because it's done by Greenfield associator.
Yes. So there are no abstractions, so it should definitely be possible. And the Feynman.
Two structures, biological structure.
I would like to discuss this topic at greater length, but sorry, here's the hook.
But what about C equal 2 and H equal 1, for example?
Right, that's my next blackboard. Yes.
Should be a affine quantum group.
So you can get things like the Youngian from that. Yes. So I would like to switch gears to theories in 4 dimensions which have one holomorphic direction and 2 topological directions. So you have an R2 times C. Now, and because of the theorem that we just discussed, you can write actions for these theories without having many concerns. The simplest action was studied by Kevin Costello to great effect. No, it's a holomorphic topological Chern-Simons theory. Yes. This theory depends on the choice of one form, so it doesn't have rotational symmetry on C, unfortunately. Well, it's a fact. Well, if it's fortunate or unfortunate. Here we take C to be valued in the Lie algebra of some semi-simple Lie algebra.
So if you want to put it on a Riemann surface, you need to have a non-vanishing one form? Or?
Yes, that's right. So, well, there are all sorts of subtleties. You can sometimes manage to put it with vanishing one forms, but you need to put some complicated defects at that location. But the most standard option is to put it on C star or the elliptic curve.
Zero beyond the...
Right, and so now...
You can also put it on a affine curve, which is not... right? If you could have any Riemann surface, if you take away several points, it can have a non-vanishing one form.
True. That's true. So which sort of mathematical structures can we attach to these theories? I could say an holomorphic topological factorization algebra in R2 times C. Something which is particularly interesting to me is that I can look at one-dimensional defects in here, so lines in R2, and these lines are sort of elements of a category. This category has it's a holomorphic topological factorization category in the transverse directions. Again, this is it's a big mouthful. You can sort of pick inside the structure of a monoidal category to start with, and then try to figure out what extra mileage you can get from the complex direction. I mean, you can have lines, and you can fuse the lines. And then you might perhaps ask if you can translate lines in the complex direction, and what happens if you fuse lines that are at different positions in the holomorphic direction. So Kevin showed that this category of lines for this action is modules for the Youngian. And a lot of beautiful structures you find in the Youngian, the coproduct and holomorphic R matrix and so on, are an expression of this holomorphic topological factorization structure. Now,
C is valued in a Lie algebra?
Yes, C is valued in a semi-simple Lie algebra, and it's a sum of forms. So there is sort of a C0, which is a ghost. There is C1, which is the actual connection, and so on. Now, but this theory is not a twist of a supersymmetric quantum field theory. So it's very interesting mathematically. You can get a lot of integrability too out of it. So the physics you get from the theory is that sometimes you can get integrable systems just because there is a Youngian. But I'm interested in, well, the twist of some supersymmetric theories. And in particular, if you take something called four-dimensional n equal to supersymmetric quantum field theories, there is a twist which sends you to this sort of h equal to 1, t equal to 2 twisted quantum field theory. Now, this is the world where Solomon crossing formula works and things like that, cluster algebras, a lot of interesting mathematics. So I would like to discuss briefly how this mathematics can embed in the world of holomorphic topological quantum field theories. So how do I present to you one of these theories? There are actually many different ways. We don't have a universal construction for all quantum field theories. One way to present such a theory is to give me a gauge group and a matter representation. So M is a symplectic finite dimensional representation of G, and G is some semi-simple reductive group. There are other constructions. There is also called the class S construction, which I will come back to later. Then a lot of these theories happen to have an extra structure, so the cluster structure that I will perhaps discuss briefly. And the basic question is sort of how do these pictures translate after holomorphic topological twist?
But also this 4D gives integrable systems, yeah? Can you
potentially
start this complex integrable system in some way direct?
Right. Well, that's a cluster data. Right. So it's
No.
Class S as well.
Everything.
Kitchen system.
okay. That's fine. I can put another blob, which is complex integrable systems.
Maybe easy way to say it is to start with complex integrable systems.
It
Then you say that this is a vacuum library with an
Yeah. The point is that holomorphic-topological twist is something I can do to a full-fledged four-dimensional theory. So these thick lines denote constructions of a theory. The dotted line denote properties of a theory. So to each theory you can associate a complex integrable system, but we don't know which complex integrable systems. I mean, some complex integrable systems might not come from a theory. Or I can associate cluster seeds to theories, but not all cluster seeds come from a theory.
each of these guys comes with a prepotential. And once complex integrable system is prepotential, you can ask which gauge theory has same prepotential.
Sure, but how do you know?
We generally don't know, but once things, both of them come with natural prepotential.
Because gauge theories are a very small subset of all theories. Class S theories are a bigger subset, but it's still not obvious that it's it's a Lampos effect, sort of issue here. So Curtis and Williams, a few years ago, gave an answer to this blob. Building on the work of other authors. I'm sorry, I'm really too short on time to be fair with the references. But they define a category of causal perverse coherent sheaves on the fine Grassmannian. It's a nice category with a monoidal structure. It has some kind of factorization algebra structure in an extra complex direction. And it's the natural candidate for representing lines in theories that live in this blob. So there is, a solid mathematical anchor from which I can start. What about classes theories?
And for this one, you don't need one form on the complex line.
No, that's right. So these theories don't require a form. So the action, let me write the action. The action looks like it's a BF theory. Sort of. So you can.
What is this symbol?
So there is this funny differential, which is sum of the Ram and Hodge. There is the gauge field. There is a a dual field to the gauge field. And then there are extra fermionic fields which are valued in this representation M.
So this refers to which? To which?
Oh, this is for the G, M theories, because they were Lagrangian. So you see, you can say B is a one form, and mu is a half density, and then this makes sense without a choice of a one form. So this gives the lines for these theories are monoidal and have a C star action of rotations of the complex plane. And an important invariant of this, or property of this category, is the K-theory of this category. Systemic invariant K-theory. Because this is monoidal category, this is an algebra. And I can tell you what are these algebras. Here the algebra is K-theoretic BFN. So Brava, Ficker, Nakajima have a construction of Coulomb branch algebras from K-theory and the fine Grassmannian, and they define a nice algebra. Here, class S theories are labeled by an ADE Lie algebra and a topological curve. and the K-theory is the skein algebra. So whatever is the category, it's a category whose K-theory is the skein algebra. And
With quantization of character variety.
yes, yes. So the skein algebra is an interesting object, a lot of applications. I would think that the category which categorifies the skein algebra should have interesting applications. I can perhaps say something more about this.
Q and Countess and Williams correspond to the loop rotation.
Yes, yes. So
K is just a formal parameter.
yeah, it's the Q of the skein algebra. So when you write relations like
So your t equal to 2, which should suggest that somehow this tensor product should be commutative. But apparently...
No. So see, the lines live the lines in R2, the lines are aligned. And so you can fuse them, but there is no way to run across each other. If you move them in the complex direction, you can move them across each other. If you work equivalently at the rotations, then you cannot, because you cannot bring them away from the origin of the complex plane. So that's why the K-theory is, the systemic equivalent K-theory is non-commutative. If you turn off the non-commutativity, the equivalent parameter, then you get a commutative algebra, which is, functions on the character variety or things like that.
So this is similar like for Yangian also, there is a way to make it non-commutative, which is worked out by Hernandez. And this also comes from something like this?
Right, so in this category, we expect to have a translation functor of some sort, so that you can translate a line away from the origin. And then the tensor product of lines at different positions should have an R matrix, but should be meromorphic in this translation parameter.
And if you account for the poles, you can make it non-commutative.
Yes, that's right. So for example, you'll typically find formula where the tensor product in one direction is maybe an extension of things. And in the opposite direction is a similar extension, but maybe it swaps around the terms and gives some C-star gradient shifts. Okay. I want to comment a little bit more on this class S. And then so the class S theories are supposed to come from a six-dimensional theory. There should be six-dimensional supersymmetric quantum field theories labeled just by Lie algebra, an ADE Lie algebra. And they should have a twist where H is 1 and T is 4. Very mysterious six-dimensional theory. Let me call this T of G. Now, the class S theories are essentially an evaluation of this topological theory on a topological surface. So Z on C, Z of T of G on C gives you the 4D theory. This one of the pieces of data of this theory should be a two category. There should be two-dimensional defects whose objects are representations of G. So this should have a factorization algebra structure with H equal to 1 and T equal to 2. And when you sort of evaluate this two category on a surface and wrap your defects on lines or skeins, you should get this categorification of the skein algebra. This is the same gadget which presumably lies behind Kovanov homology.
If is it known what the category?
No clue. So if you can guess a cool two category of representations of an ideal algebra, let me know. Especially if it has an holomorphic-topological factorization structure in a lot of directions. Okay, so
Is it related to work of Igor Frenkel and Turay in the 90s, which
I don't know.
they tried to have a four-dimensional analog of Shetikhin-Turay invariance using affine quantum groups. And, there were some non-trivial.
That sounds more like Kevin's theory on C star times R2. That will give you your Q G hat. This has more dimensions. Right, so how does it connect to work by Maxime? So what I've been trying to do with some co-authors over the last year or so is to try to figure out what the holomorphic topological twist of that blob is. So I want some kind of categories, a category labeled by the cluster seed, which I can encode into a quiver. A category which has all of these beautiful structures. And what this overlap means is that there are expected to be RG functors. So sometimes you can associate a cluster seed to one of these objects, and then there should be a functor between the corresponding categories, monoidal, star equivariant, and so on. So how do I get a category out of a cluster seed? So Maxime and Jan at some point defined the cohomological whole algebra. This is an algebra which is supposed to know about BPS particles in these four-dimensional inequality theories. It's somehow supposed to capture some aspects of this effective description of the four-dimensional theory. And the proposal that we have developed is the following, is that there is a category of bimodules for the coha. Perhaps it's some equivariant condition that I'm not going to try to describe. And that this category of bimodules should be the lines associated to this cluster seed. These bimodules are constructed in a similar way as the coha. So the coha is built by so essentially looking at equivariant cohomology of representations of your quiver. I'm not going to try to write a formula with superpotential. Let's write. Right, this construction requires a superpotential, but it should be independent of superpotential as long as it's generic. So I will only assume that always assume that there is a generic superpotential. In particular, you can take your original quiver, a bunch of nodes and arrows, and add an extra node with a certain number of arrows to it. Let me call it this number of arrows L1, L2, and so on. And there is a way to associate to this a bimodule. So, yeah, so in the literature, people like to take frame representations, so a stable frame representation of this quiver, and that gives a module for the coha. But if you just take all representation, do the same thing you do for the coha, you can get a bimodule. It's much bigger. It's free over the algebra typically. And if you sort of tensor it with the algebra with C over the algebra, you can get what people like to study. And
Is it just the cohar of the bigger quiver? Or?
It's a piece. That's right. You take you put rank 1 here. You don't put equivalent parameters there, and that's the cohar for the bigger quiver. That's a piece, and that's why it's a bimodule for the cohar. And experimentally, I mean, I'm not very good at proofs, but experimentally, the tensor products. So this category is monoidal because it's bimodules, and I can do tensor products of bimodules for the cohar. And experimentally, you get extensions of some other B's. So it looks like there is some nice monoidal category of bimodules which have this origin.
I mean, finite extension, yeah?
Yes, finite extensions. And essentially by construction, at the level of K-theory, this matches everything that is known about cluster algebras. So again, I really want to, I mean, I have a limited amount of time, but there is some kind of graded character of these bimodules.
But these B's are they are not simple, right?
No, as modules or
No, they're dualizable.
So when you say that it's an extension of B's, I mean, there's a notion of character which would guarantee that any two representations of it as extension of B's has the same, like Jordan-Holder property. There are the same multiplicity.
This is purely experimental. So I literally took a bunch of these bimodules and I tensored them and I found maps to write them as extensions. So I don't have any conceptual understanding.
It is not clear at the moment whether there could be two such representations which would have different multiplicities.
Possible. So the guiding principle is that the characters of these bimodules look like some objects times the character of the cohar. And these objects are what's called cluster functions. So the quantized functions on the character on the cluster variety. And this is set up in such a way that when I tensor bimodules, the functions multiply.
Are these functions linearly independent for different elements?
Yes.
Okay, so then it guarantees that the two decompositions
Is
will
it kind of like for control basis? Yeah.
Yes. So these are the Laurent polynomials and cluster variables which remain such in all after all mutations. And it sort of follows from general cohar machinery. There is a Harder-Narasimha filtration of B that shows that this is really a tensor product of this form. And when you mutate the quiver, the whole expression, the character gets conjugated by quantum logarithm. And anyway, so you get all the cluster properties for free. So this looks like a cool, a potential categorification of the whole cluster machinery.
But this is not, extensions are not split, yes?
Right. So in concrete examples, you find extensions which are they're not split. And so the sort of experiments we're trying to do now is to find situations where you have both a Cartesian description and this description. We know the map from the level of objects. So we can take tensor products in Cartesian-William and you find a certain exact sequence. You do the tensor product by modules, you find the same exact sequence, hopefully. So we are sort of trying to accumulate examples.
And these bimodules, are they free on one side?
Yes.
So the tensor product is exact?
Yes. Yeah, they are dualizable bimodules. And there is a whole story about some equivariance under some group action here that I'm ignoring, but it's probably important. I would really like to have some feedback or to see some theorems proved about these bimodules. Okay. I still have 5 minutes. I want to describe a third topic very fast. So let's take this general action that I was writing somewhere. But let me take fields which are matrices, n by n matrices, times some auxiliary vector space. So I have an action like trace, and I want to write a single trace action. So something like trace of phi de phi plus some single trace, some polynomial of this phi subject to a trace, where I use matrix multiplication.
What does it mean, auxiliary vector space? It means this is like several phi?
Yeah, it means I have several phi's, which each of which is an n by n matrix, and I multiply them as matrices. So whenever I have a situation like that, I put a 1 over h bar in front, why not? Whenever I have a theory of large matrices, I can do what's called the Hooft expansion, meaning I can try to write everything in a way that is independent of n, like write all operators as products of matrices, ignoring trace relations momentarily, and send n to infinity as I send h bar to 0, but I keep h bar n fixed. This is the glib way to describe it. I could try to do better, but time is what it is. A universal principle of string theory is that whenever you take a quantum field theory and you do a Hooft expansion, the result should be a string theory. This should be true for every quantum field theory, in particular for these holomorphic topological theories.
So I will be cyclic functions.
Yes, that's right.
So you mean that Feynman diagrams will be surfaces now?
Yes, that's right. So what's going on is that when you do perturbative calculations in this theory, you get Feynman diagrams, which can be represented as ribbon graphs. And you want to sort of, at the leading order, you're going to take the planar ones, things that look like a union of spheres. And then there's going to be an h bar squared non-planar. I mean, in general, there's going to be some power of h bar in front of your calculation, and then bigger powers as you look at non-planar things. And this is supposed to match the genus expansion of a string theory. Now, if you think about this, this is crazy because there is so much freedom here, right? You can write all sorts of different Lagrangians, all different sort of quantum field theories, and somehow I should be able to produce for you corresponding amount of string theories.
But when you do this expansion, these surfaces are kind of topological, and in string theory they are complex surfaces.
Well, actually, in string theory we often work in conformal gauge, as you're saying, meaning we take a conformal field theory and then we couple it to Gauss to get the worldsheet theory. When we couple it to Gauss, we actually kill the holomorphic dependence. So the worldsheet theory of a string theory is topological on the worldsheet. And the moduli space of complex structures is actually like a contraction of the space of surfaces. You don't need to think about complex structures. So string theory, it should be possible to define string theory given any topological worldsheet theory. And we were discussing before that topological theories in two dimensions can be described mathematically in terms of categories and things like that.
So you mean that when you take semi-infinite cohomology, then the Rasor algebra acts trivially on the cohomology?
Yes.
Because any algebra acts trivially on its cohomology.
Yes. So I feel that morally speaking, I should be able to give you a string theory by giving you a category, the category of branes for the worldsheet theory. I don't know if this is actually true, because there are a lot of subtleties in integrating over the moduli space of complex structures. But at least as a philosophical principle, I would like to be able to take the data, the combinatorial data of this theory, and spit out the combinatorial data of some category
That would mean that
of branes.
closed string theories are contained in theory of transformation.
Yeah. Yes. Now, to be shouldn't say, okay, I'm out of time, so I shouldn't say that, but I'll discuss later. All I want to say now is that for holomorphic topological theories in particular, the two sides of this should be completely mathematically rigorous. So, and you can already kind of see the string theory and the categorical structure here. See, this action essentially defines for you an infinity category. Just that it Calabi-Yau infinity category, just because it's a, it's a collection of linear functionals on your A, which has a cyclicity property. They define a BRST operator, which maps phi to some polynomial in the phi's, some. So you kind of see that there is an odd, non-commutative odd vector field, which means that there is an infinity algebra. So here there is already kind of a brain of some sort.
How many dimensions?
It varies as a function of h and t. Yes, so morally speaking, before you do any interactions, if you try to set lambda equal to 0, you can just use methods of homological algebra to recognize that the Largen limit is giving you the standard things like single trace operators are cyclic homology of the infinity algebra, and so on. You can find the Gerstenhaber bracket. You can add fundamental matter to find other modules for this infinity algebra and find the category of modules. And all of this construction reproduce sort of the lambda to 0 limit of the 't Hooft expansion. So at lambda equal to 0, you sort of have a string theory in some mysterious non-commutative Calabi-Yau times r to the t, c to the h. And now the name of the game is to figure out how the planar correction deformed this manifold. So you should be able to go from this manifold to some mysterious non-commutative Calabi-Yau y by some kind of a geometric transition, perhaps, which reproduces this perturbative expansion. And in particular, classically, it reproduces the planar limit. So homomorphic topological string theories in the perturbation theory, completely mathematically rigorous. Classical string theory based on a DG category, mathematically rigorous. So there should be a theorem that the planar limit of this gives you that. And I've been trying to explore simple examples of this. The case I'm looking at recently is just the case of chiral algebras.
So it is rigorous because there is no divergences in Feynman diagrams.
There are, but they are known. I mean,
you can know how to deal with it.
That's right. So you can just write Feynman diagrams that are finite. Right? Exactly. So here you have a chiral algebra of large matrices, and you can show that the data in an action is the same as the data of a 2D Calabi-Yau cone, non-commutative. So you have something like C times X 2D. And what's morally speaking is happening is that you can sort of complete this to a kind of resolved conifold geometry, a non-commutative resolved conifold, like a fibration of X 2D over CP1. And then there should be a geometric transition.
So it's C Calabi-Yau.
Yes. To some kind of Y3D. And so I've been trying to sort of find Y3D, find a categorical description of this Y3D, and I think it's reasonable. It seems to work. You can really find the category by studying mesonic operator. The trick seems to be to add extra vectorial matter. You add vectorial matter in many different ways. This gives you many different D-branes in your string theory. You get the whole category of D-branes. Because unfortunately, the original D-branes typically disappear. So you start with the categorical description at lambda equal to 0. But the first thing that holography does is that it destroys the original d-brane and replaces it with some new geometry. So those are gone. The trick is to produce new d-branes and then see how those are deformed. Anyway, I can give you some details, but I think I'm out of time.
So let's say that I think the statement that you made about Maxime, that his work for the last few years always runs into stuff that Maxime did, is also true when Maxime replaced with Davide and Davide replaced with me. I have been running into his work anytime I do something. So, any questions?
Your geometric transition is not really geometric because it involves non-commutative.
Yes, if x2 is C2, then it's a standard geometric transition of C2 mod gamma.
In your depiction, the class S bubble is not contained in the cluster bubble, this intersection. Wouldn't the work for Goncharov, and more recently Goncharov-Shen, tell us that for every surface and simply lays the group there is some cluster story, so it should be a sub?
I get confused by surfaces without punctures. Like Sasha.
Because
yes.
fundamental group is not free.
Right. So if your Riemann surface has no punctures at all, can you find a cluster structure?
It's not cluster.
Right. It's some kind of a limiting.
Maybe one can get out, but it's not clustered.
Yes, exactly.
These intersections are very large. Maybe at least the large subset of the class S.
Yes, no, absolutely. So this cluster blob is supposed to cover almost everything.
Is it possible to talk about the intersection of the GM and the class S? Is that quite a large intersection? Or?
For SU for class A1, so when the Lie algebra in class S is A1, it's very large. So as long as you don't have irregular singularities of excessive degree, you can give a G and an M. If you look at other Lie algebras, you need to put very severe restrictions on the punctures that you allow.
If I understand correctly, in each picture there's supposed to be 3 types of Coulomb branches. If you compactify on R4 or R3 cross S1 or R3, is it understood in all of those cases what those 3 types of Coulomb branches are?
Well, from the cluster description, you can get the Coulomb branch in generic complex structure. You don't get the subaggregate integrable system. You can start talking about stability conditions and.
Hold on. So if I start with class S, is it possible to describe what those 3?
Yes.
And what are they? Or?
So it's just the Hitchin modular space.
So that's the one compactified on R3 cross S1, and then there's the R3 picture and the.
No, there is no R3 picture. See. Unfortunately, there is a misnomer in the mathematical literature. People talk about the K-theoretic Coulomb branch of 3D theories. That's not right. What you're really talking about is the K-theoretic Coulomb branch of a 4D theory, which has the same gauge group and matter representation as the 3D theory. But that's not a thing. It's when you have Lagrangians, you can say, okay, I use the same ingredients to build a Lagrangian. But there is no sense that there is a 3D theory that is a 3D version of class S theory.
But if you look at the examples in the Seidberg and Witten papers, there's like NF equals 0, 1, 2, 3, 4 there. They do describe these 3 different pictures there.
Yes, because...
Class S or GM?
Yeah, those belong to class S, but the 3D limit is essentially focusing on a singular locus of the character variety. It's not clear to me that that singular locus is always uniquely determined, and sometimes there is no singular locus. So if your character variety has a big conical singularity, you can focus on the cone and call that a 3D Coulomb
So
branch.
in those cases, they're spaces of Stokes data. They have irregular poles, and there's like an additive moduli space, and the R3 one looks as if it's isomorphic to that. Does that hold always, or just in particular cases?
Well, I'm not sure there is a canonical way to linearize the story, to pick a point. It's like physically you're trying to say, okay, take the 4D theory, compactify it on a circle, and go at low energy. Like make the circle very small.
Right, so geometrically it should be the complement of the theta divisor. There's a canonical divisor and you delete that.
Okay, no, if you have a canonical place you like in the for the geometry, you can surely call the log the linearization around that, the 3D Coulomb branch. Mm-hmm. Okay.
Okay, let's thank the speaker.